Okay, so continuing our discussion of the 1D wave equation into which we will apply the FEM. Okay, so far we have not come to the FEM, we have just discussed the wave equation and shown you the boundary condition that is required, right? And we said that this is a new kind of boundary condition, not Dirichlet, not Neumann, but a combination of the two, which is called the Robin boundary condition, okay, or Sommerfeld radiation condition. So, this boundary condition is very important in almost all electromagnetic scattering problems. In 1D it looks very simple. So, what is it saying? Derivative, spatial derivative of the field is proportional to the field, that is what it is saying, right. What will happen in 2D or 3D? This derivative will get replaced by curl, and the del will appear over there, right. So, we have to keep in mind that. So, do not get, you should not get overwhelmed when you see an expression in multiple dimensions. When you look at it in lower dimensions, this is basically what it is. Gradient of field is proportional to the field itself. And why is this sort of very important is because what is it saying? This is the condition obeyed by a wave in free space at any point in free space. Agreed? So, when we are, so let's take a general example. Let's say that I have an antenna, let's say that's your Wi-Fi antenna over here, okay, and you have some human being over here. You could even have a mobile phone in his hand, his or her hand, and we are wanting to study a very important problem. All of us know that mobile phone radiation is a possible cause for concern, health issues. So, we want to simulate how much is the field that is entering the tissue, how much is the maximum power level and all of those things. So, when you go to try to solve this problem in a simulation, you have to end the simulation boundary somewhere, right. So, you can for example say that this is going to be my simulation boundary, okay. So, let us say in this problem you want to study two things. One is how close should you be to the base station to be safe. We know that base stations, the towers, they put out a lot of power. So, if you spend too much time in front of them, there is a health risk which empirically has been observed. On the other hand, someone carrying the mobile next to their hand and talking for extended period of time, mobile produces less power, but if you keep it held for a long time, that is also a possible cause for concern. Now, to solve this simulation, you need to terminate the boundary somewhere, otherwise you cannot simulate infinite space. So, let us say you decided to terminate it here. Now, this boundary that you have put over here, is it a real boundary or a hypothetical boundary? It is a hypothetical boundary. In the actual problem it is not there, but I had to put it there. So, whatever field is, let us say, emanating from this domain, when it encounters this boundary, what should happen in real life? It will keep going, this wave will keep going because this boundary does not actually exist. But mathematically, when I end my boundary over here, what will happen? It should go to 0, or, well, if it goes to 0, there is a problem. Because for a physical field cannot abruptly go to 0. Exponentially decay, you want the field to exponentially decay before the boundary? At the boundary you want the field to go to 0. Okay, so let me give you an example. This is a before the boundary it should exponentially go to 0. Okay, so let us see the problem with that. Let us say that this part of the boundary over here is made out of this green part. Supposing I made it out of perfect metal. So, what will happen to a field when it hits there? It will bounce back, but the field goes to 0, right? Which is what you wanted. So, is that desirable or undesirable? Field went to 0 like you wanted at the boundary, but is it desirable or undesirable? So, it is undesirable because by putting a metal, what are you doing? Even though the field at the boundary has gone to 0, the way it does it is by generating an equal and opposite field. So, what will happen is that by putting a metal over here, there is going to be a reflection from there, which was not there in the physical problem. So, setting the field to be 0 on the boundary is not the correct boundary condition. What is the correct boundary condition? Nothing should get reflected back in. If that happens, then I am happy, whatever be the magnitude, as long as it does not come back to me, then I am happy. Then I am recreating the real world problem as far as possible, right. So, what I want is that this field should come over here and just go off. There should be nothing that is going back. right. So, at this boundary over here, if I impose this condition, what is it recreating in some sense? This is the condition that is obeyed by a wave travelling unhindered, unobstructed. And if I am able to impose this condition at that interface, it will try to recreate the same situation. That the field is, because it looks at this, it says, yeah, the field is supposed to go on because that's the equation obeyed by a plane wave that is travelling unbound, right. So, that is why this, that is why the name radiation boundary condition has come from the scattering people, because for them this is a radiation boundary condition, meaning it is simulating a radiation that is going off to infinity. Circuits people call it impedance boundary condition for different reasons, okay. But the physical interpretation is this: I do not want the field to come back from a hypothetical non-existent surface, okay. So, this is the motivation we will carry to 1D, 2D, 3D, whatever, how many ever dimensions we are solving the problem. So, the question is that, is this boundary condition dependent on the boundary location? So, is it? Look at the boundary condition. Does it depend on the location of the boundary? Why? Because it depends on u of x. So, at whatever x I am, I put this, right. So, it is not independent. I am not setting, unlike the Dirichlet and Neumann boundary conditions, where I am setting u of x equal to constant or du by dx equal to constant. That seems to not depend on where I am. But on the other hand, this boundary condition, it adapts to where I am, because u of x and du by dx both are together being set to 0. So, you can impose it at 1 meter, you can impose it at 3 meters from the object. What is the disadvantage of imposing it at 3 meters? Extra computation for no need, right. So, supposing this was your boundary, I can as well say, oh, I want to make this boundary. Sure, do it, no problem. For no good reason, you are simulating all of this extra space. Extra space translates to, extra physical space translates to larger computational domain, larger size of matrix, more computation time, more RAM, everything, for no good reason. There is no exciting physics happening in this region. Why bother? So, in fact, one of the considerations in designing boundary conditions is, how can I get my mathematical boundary as close as possible to the object to minimize computation time yet retaining accuracy. So, that is a very common requirement, okay. Yeah, so in 1D this is an exact boundary condition, okay, it is exactly satisfied. We will see that this boundary condition in higher dimensions has an inaccuracy in it, okay, but we will come to that. Alright, so let us continue with our wave equation. So, I have told you about the boundary condition, and now what remains is to take our differential equation and convert it into the FEM form, right. So, let us start that. So, what is the first thing I have to do? Take the differential equation and find its residual, right, weighted residual. So, weight, residue, integrate, okay. So, let us put the integration sign first, okay. So, let us call the weighting function W, okay. And what is the residual in this case? Okay, so let us just write it as u double prime x plus k squared ux minus 0, there is no right hand side right now, okay. Okay, so this is just the definition of FEM. Take your weighting function, take your residual, integrate. The W's are going to be the weighting functions for each segment. I will define it. I have not yet substituted the basis functions, okay. Next step, step 2, we discussed this previously. What do I do next? Converting to weak form. So, that is basically integration by parts, right. So, what do we do now? There is a double derivative term over there, right. So, that can get converted how? So, one integration is going to help me with that. So, this will become W x u prime x endpoints minus w prime x u prime x dx, correct, plus k squared wx ux dx equal to 0. Okay. So, this was weighted residual and this is, and as we discussed earlier, this weak form is useful because it involves only first order derivatives. Okay. I have not put the limits of integration, but they correspond to the domain of W. That's implicit. Okay. So, now let's proceed further. Let's now put in, now what is it that we have to choose? We have to choose W's and we have to choose U's, correct.